Greetings, Internet users. It is often said that the temperature in space is very low since we are outside Earth's atmosphere, and everything should freeze due to the higher altitude. Scientists have measured the temperature of the universe using the COBE satellite, which performed a specific measurement and resulted in an average of about 2.7 Kelvin, approximately minus 270 degrees Celsius. This temperature has changed over time, and it is believed to have been much hotter in the beginning due to massive stars and quasars emitting a significant amount of energy, with matter being more concentrated in a smaller space. Now, as the universe has expanded, it has been estimated that it loses temperature. If that's the case, how is it possible that space is so cold, and why doesn't the sun, which has a temperature of 5,500 degrees Celsius, heat up our nearby space? It's rather peculiar, and it makes us wonder why, when we climb mountains, the temperature progressively decreases instead of increasing logically, as one might expect to get closer to the sun. It appears as if there is no fixed temperature in the universe, and certain objects heat up while others do not. The sun should be affected by the extreme coldness of space. So, is the sun really hot, or is it cold? It's hard to imagine space being at minus 270 degrees Celsius, but that measurement is deceptive since it refers to the vacuum of space where there are no stars emitting heat. Heat is defined as the vibration of atoms and molecules in motion within an object. In space, there is barely any interaction with these particles as it is a very low-density region. The majority of the heat in the universe comes from stars, and to a much lesser extent, from planets and other objects. The sun is not a ball of gas and fire. In space, there can be no fire as there is no oxygen. The correct term is that the sun is a sphere of plasma and gas where nuclear fusion takes place in its core. These temperatures can reach up to 15 million degrees Celsius. The energy from the fusion of atoms in the sun produces heat, but how does it transmit that heat to space if there is no dense air? The reason is that heat is transferred in three ways: conduction, convection, and radiation. Heat transfer by conduction occurs through direct contact between a solid body with a higher temperature and another with a lower temperature. Heat transfer by convection occurs through liquids and gases, transferring heat from one place to another. In the vacuum of space, heat can only be transferred by radiation through electromagnetic waves. If these waves encounter an object in their path, the object heats up by absorbing the photons. This heat transfer only works if there is an object in the path of the photons. It means that it doesn't heat up the entire space around it, only the objects within the zone of light, and its effect diminishes with distance from the source. Astronauts who have been in Earth's orbit have measured temperatures in the shadow zone as low as minus 180 degrees Celsius and up to 122 degrees in the sunlit zone. That's one of the reasons why astronauts wear thermal suits, usually white, to reflect most of the solar radiation. Assuming they spend most of their time in the sunlit zone, if they were to enter the shadow zone, they wouldn't freeze rapidly since the accumulated heat gradually radiates into space. Now, it's the astronaut who transfers heat to nearby objects. However, compared to the sun, this radiation is practically non-existent due to the thermal protection of the suits and the slow transfer and emission of heat. In space, the heat from objects is emitted in the form of infrared radiation, and it's through other bodies that we can measure this temperature. For example, on Mercury, temperatures in the shadow zone can reach minus 180 degrees Celsius, and up to 427 degrees in the sunlit zone where photons are absorbed. Venus, on the other hand, experiences something extraordinary with its atmosphere that is 90 times denser than Earth's. Heat reaches Venus through radiation and is trapped in its dense carbon dioxide atmosphere, transferring through convection and conduction from one place to another on the planet. This creates a greenhouse effect, causing temperatures to rise to 462 degrees Celsius, far exceeding Mercury's temperature, as heat circulates within its dense atmosphere, preventing any point on the surface from dropping below 400 degrees Celsius. In our world, on Earth, there is also a curious phenomenon. The heat from the sun reaches the Earth in the form of radiation, and at least half of it is infrared radiation. However, the Earth is a massive ocean of air, and thanks to its atmospheric pressure and the ozone layer, it becomes habitable. The Earth's gravity is just right, allowing it not to lose too much heat to space or retain too much of it, otherwise, the Earth would lose its oxygen. Additionally, the atmosphere protects us from many types of radiation that could be harmful to living beings and allows the appropriate amount of radiation to pass through, preventing the Earth from becoming excessively hot. It acts as a kind of filter. Thus, the Earth's heat travels from one zone to another through conduction, and gas molecules transfer heat from one another through convection. This means that the Earth receives heat through radiation, convection, and conduction, creating a perfect balance in the Earth's atmosphere at an average of 14 degrees Celsius. Even during the night, light, the temperature does not drop excessively due to this equilibrium. However, human activity is changing this delicate balance that sustains life. Moreover, inside the Earth, there is a core with temperatures reaching 6,000 degrees Celsius, higher than the surface of the Sun, and it transmits some geothermal energy through conduction and convection within the Earth's bodies. Although most of the temperature comes from the Sun's energy, if the outer core didn't heat the liquid, we wouldn't have a magnetic field, and the atmosphere would be flooded with harmful solar radiation. Our existence is thanks to the atmosphere, which allows solar radiation in the form of visible and infrared light, and the active terrestrial core. Sun rays also transmit heat to the Earth's surface, and part of it is radiated back into space as infrared rays. However, certain gases in the atmosphere, such as carbon dioxide, water vapor, and methane, allow visible light to pass through but absorb infrared light, preventing more heat from escaping than it should. These greenhouse gases from fossil fuels contribute to disrupting the Earth's balance and retaining more heat. Over time, the Earth is gradually warming. It is good to have some greenhouse gases to retain heat, otherwise, the Earth's atmosphere would have an average temperature of -16 degrees Celsius. Without an atmosphere retaining heat, it would resemble Venus, but with much less of a greenhouse effect. When the sun rays reach the Earth's surface, some of the heat is radiated back into space in the form of infrared rays. However, certain gases in the atmosphere, such as carbon dioxide, water vapor, and methane, allow visible light to pass through but absorb infrared light. This prevents more heat from escaping than it should. Greenhouse gases from fossil fuels contribute to disrupting the Earth's balance and retaining more heat. As a result, over the years, the Earth is gradually warming. It is beneficial to have some greenhouse gases to retain heat, otherwise, the Earth's atmosphere would have an average temperature of -16 degrees Celsius. Without an atmosphere retaining heat, it would resemble the Moon, with temperatures of 122 degrees Celsius in the daytime and -170 degrees Celsius in the shadow. Moreover, the Sun is 150 million kilometers away, making a mountain at 5,000 meters of altitude insignificantly different in temperature from the Sun. The atmospheric pressure and the Sun's influence result in the climate we experience. When sunlight passes through the atmosphere, it heats the Earth's surface and sends heat to air molecules. As these molecules rise, expand, and cool down, the gas masses transport the heat from one place to another. This heat transfer process is called convection and is crucial for the Earth's climate, distributing heat everywhere, as long as there is sufficient atmospheric pressure. As we ascend in altitude, the temperature decreases, but Earth's atmospheric layers are complex. Depending on their nature, at different altitudes, they allow more or less radiation to pass through, leading to significant temperature variations in the form of an S shape. For instance, in the stratosphere, from about 10 kilometers up to 50 kilometers in altitude, as we ascend, ultraviolet rays transform oxygen into ozone, a process that ionizes the air, producing heat. One of the upper layers of the atmosphere, the thermosphere, beginning at around 100 kilometers up to 1,000 kilometers, reaches temperatures of 122 degrees Celsius in the illuminated zone, and almost all the sun's heat is transmitted through radiation. This is where the International Space Station and the Hubble telescope are located. Despite the advances in astronomy and our knowledge of the Earth's atmosphere and geology, many myths about the sun, its temperature, and space still persist. For example, the misconception that the moon has a hidden side that never faces the sun, referred to as the dark side, when, in reality, it is merely the side we don't see from Earth due to synchronous rotation. Similarly, the idea that we would freeze instantly if we were exposed to space or that the sun is a ball of fire is not accurate. In space, there is neither cold nor heat if there is no object to absorb electromagnetic radiation traveling at the speed of light. The temperature of space is an illusion, and the estimated -270 degrees Celsius in the vast vacuum of space is a reference to any imaginary object, as there would be no observer or measurement interacting with the environment. It would be as if nothing existed. In space, if you place an object in the dark, it will radiate heat in the form of electromagnetic waves according to its temperature. Any object with a temperature higher than absolute zero, which is -273.15 degrees Celsius, emits heat. This emission of heat causes the object's temperature to decrease over time. Without a source of heat like a star, the object would cool down significantly. However, something as hot as the sun, continuously emitting energy through nuclear reactions, is not affected by the emptiness of space. On the other hand, if such an object encounters a star that sends electromagnetic radiation, the object will absorb those photons and heat up. The closer it gets to the light source, the higher its temperature will increase. If the object were to reach the same temperature as the star, an equilibrium would be reached, as the energy received would be equal to the energy radiated. This is how temperature works in space. Hot bodies transmit radiation to colder ones through the vacuum, a way of balancing the universal machinery. In reality, space itself has no particular temperature. Our beautiful home planet, Earth, with its perfect thermal balance, helps redistribute heat, ensuring that we neither freeze nor scorch. It is a rarity in the cosmic ocean filled with radiation, where Earth acts as a filter, providing us with what we need to live. If you enjoyed this video, please like, subscribe, share on social media, and leave your comments.